Hello everyone. Today let's solve the problem number 23. Merge k sorted lists. Right. So what the question states here, we are given an array of k linked lists. Each linked list is sorted in ascending order. You can clearly see here 1, 4, 5, 1, 3, 4 and 2, 6. This is sorted in the ascending order. Right. So we have to merge all the linked lists into one sorted linked list and return it. We have to merge all the linked list, means this one, and third list, right? These three things, these three linked lists, we have to merge all the linked lists into one sorted list. Means these three we have to merge into single sorted list. Again, this has to be in the ascending order and then return it. That's what they have asked in the question. So just give me a second here. This one, when we merge, see here 1, 4, 5, 1, 3, 4, this one is 2, 6, right? So when we merge here, this one first, it will be 1, 1, 2, right? Next, this will be 4, 3, right? 4, 3, then 6, 4, 3, 6, and finally 5, 4, 5, 4, and they have asked us to sort in the ascending order. After sorting this one in the ascending order, what we get? So 1, 1, 2, 3, 4, 2, 3, 4, 5, 6, right? So this is what we get as output. So this one we will return this one in the form of output, right? 1, 1, 2, 3, 4, 4, 4, 4 we have twice here. Sorry, here I forgot 4, 4 here twice. 4, 4, 5, 6, right? So this one we have to return in the form of output. They have clearly shown here. So they have clearly explained as well. Just give me a second here. So the linked list are 1, 4, 5, 1, 3, 4, 2, 6. Merging them into one sorted list. See here 1, 1, 2, 3, 4, 4, 5, 6 unsorted. So here we have been given a empty lists, right? So here the output is empty list or empty array as well. So list here also we have got empty array, right, within the list. So the output will be empty array in this case as well, right? So I hope the question is completely clear. What we need to do is completely clear as well. Easy to understand, right? So I'll just clean up this one. No need of this one. So first thing, we will discuss the approach. After discussing the approach, let's discuss the edge cases one by one and then finally write the code and discuss the complexities for the code that we have written. Initially, as usual, let's discuss the approach first. So the first thing that we need to note down here is we'll be making use of the minimum priority queue. So we'll be going with the minimum priority queue approach or the priority queue approach, right? So the first, I have considered the same example, the first example that they have given in the question, right? So we have already discussed this one. 1, 4, 5. We have the lists here 1, 4, 5, 1, 3, 4, 2 and 6, right? So we have 1, 4, 5, 1, 3, 4, 2 and 6. When we merge this one, we get 1, 1, 2, 4, 3, 6, 5, 4. So when we sort this one in the ascending order, we get 1, 1, 2, 3, 4, 4, 5 and 6. So this is what we need to return in the form of output, right? So that's what they have written in the form of output. We have the idea right now. So let's discuss the step-by-step execution. So here the same first example I have considered. First one here is linked list. We have here as 1, 4, 5, 1, 3, 4 and 2, 6, right? So we have 1, 4, 5, 1, 3, 4 and 2, 6. We have three lists here. 1, 4, 5, 1, 3, 4 and 2, 6, right? So here the first step, we will insert we are making use of the minimum priority queue. We'll be making use of min-heap or minimum priority queue here, right? So just keep this in mind. We will insert the first node of each list. First node of each list into the min heap, right? First node of each list means I have said the same thing here. 1, 1, 2. This one, right? So that's what we have now. Just imagine that we have already inserted the first node of each list into the min heap. Now it becomes 1, 1, 2. Let's move on with the second step here. We will extract the minimum, right? So we will extract the minimum, that is nothing but 1 in this case. 1, 1, 2. What is the minimum among 1, 1, 2? 1, right? So we will add it to the result and insert the next node from the same list. So and insert the next node from the same list. When we insert the next node from the same list, it becomes 1, 2, 4, right? So it becomes 1, 2, 4, right? Minimum is 1. Next 2 we have. Next insert the node from this one. Next list means 4. So this is one list, this is one list, this is one, right? So here in this case, insert the node from the next list is this becomes 1, 2, 4, right? Minimum among 1, 1, 2 is 1. We will extract the minimum 1, add it to the result, insert the next node from the same list, right? Same list means this list we are speaking of 1, 4, 5. So we are inserting the this one next node from the same list. This becomes 1, 2, 4. This is fine. So now we will extract 1 again. So minimum among 1 to 4 is 1. We will extract 1 and we will add to the result and we will insert 3 from the same list. Insert 3 from the same list means this one I am speaking of, right? We are considering 1, 4 we have considered. Now we are considering 3. We are inserting 3 from the same list. Now this becomes 2, 3, 4. 2, 3, 4, right? Again the same step. We are doing it from the step 2 basically. We will again go for the minimum here. So minimum is 2 here in this case. We will extract 2. We will add it to the result. Now we will insert next element, nothing but 6 here. You can clearly see here. In this case 6. So first 1, next 1 we found the minimum. Here next 2, next 4, 3. In this step we are inserting 6 here. This is fine. We are inserting 6 here. So after inserting 6, this becomes 3, 4, 6. PQ consists of 3, 4, 6. Among this one, what we will do? We will in this one extract 3, as 3 is the minimum. We have to extract the minimum number. We will extract 3. We will add that one to the result. So we'll add that one to the result and we will insert the next element. Next element here is this one, 4. We will insert the next element, nothing but 4 in this case. Just give me a second here. Yeah, we'll insert 4 in this case, right? So now this becomes 4, 4, 6. So again, among 4, 4, 6, what is minimum? 4, right? So we will extract 4, minimum is 4, we will add to the result. This time we will insert 5. This time we will insert 5, right? So this time we will insert 5. So when we insert 5, this becomes 4, 4, 6. Again, we will extract 4. So we will extract 4, the final step. So extract 4, we will add to the result. This becomes 5, 6. Right? Only 2 elements are left now, 5, 6. Among 5, 6, what is minimum? 5 is minimum. We will extract 5, add to the result. Only 6 is left after extracting 5. Only 6 is left. Now, as only 6 is left in the PQ, so minimum will be 6 itself. We will be adding 6 to the result. Now this is empty. Until empty, we have to carry on each step, right? Until PQ is empty. So now the output is whatever we extracted step by step, that is stored in the result, right? First is 1, 1, 2. Here in this this one page, you can see 1, 1, 2, right? 1, 1, 2, 3, 4, 4, right? 1, 1, 2, 3, 4, 4. 1, 1, 2, 3, 4, 4 here in this case. Finally, 5, 6. 1, 1, 2, 3, 4, 4, 5 and 6. Same thing. This is the final output that we got, which is equivalent to the output that they have given for the example 1. 1, 1, 2, 3, 4, 4, 5, 6. This is the output that we got as equivalent to the output that they have given for the example 1 in the question. So the approach works absolutely correct in this case, right? So the approach works absolutely correct in this case. So here, as we are familiar with the approach, let's discuss the edge cases very quickly. I'll just come here. So the first edge case here would be, just give me a second here. The first edge case here would be empty input, right? Empty input. When I say empty input here, the list says empty. Lists are empty, right? So we don't have any lists at all. So output will be empty array or empty list itself. So no linked lists here, no link list to merge. We have to return an empty list in that case. So let's come to the second edge case here. All empty lists. So we have empty lists here within the list, right? So here in this case, even though there is one list, it is empty. You can clearly see here. We have one list here, but this one is empty, right? So we will return the empty list itself as output. So let's come to the third edge case, only one list. So when I say only one list, see here, lists, we have one list which consists of the element 1, 2, 3. So here we have only one list, we will return it as it is, right? So 1, 2, 3 will be the output in this case. Let's move on with the fourth edge case, lists with duplicates. When I say lists with duplicates, we have lists equals 1, 1 and 2, 2 here in this case. So output will be quite obviously when we merge this one. So see here, 1, 1, 2, 2. You can, if you want to know about the approach correctly, you can just try this one. The last example, this is simple example with only two lists. You can just try it out in the same way that I had shown for the example one in the approach, step by step. You can just try it out by considering this example. So I insist you to try this out so that you understand the approach clearly, right? So when we merge this one, 1, 2, 1, 2 we get. When we sort this one, it will be 1, 1, 2, 2, right? So each step will be, we had made use of the minimum priority queue. Each step I had shown, it was easy to understand, right? The approach. So in this case, it will be 1, 1, 2, 2, right? So when we sort this one, we get 1, 1, 2, 2. This is fine. So these are the 4 edge cases that we need to keep in mind. So the first edge case is for, just give me a second. The first edge case is for empty input. The second edge case is for all empty lists. So the third edge case is for only one list. And the fourth edge case is for lists with duplicates. These are the 4 edge cases that we need to keep in mind. I hope this is completely clear, right? So now we are completely familiar with the approach as well as the this one, edge cases, right? As we are familiar with the approach and edge cases, it will be easier to write the code. Let's start writing the. So let's go with the first step here. We'll be making use of the min heap or minimum priority queue to store the nodes based on their values. So we have already discussed this one multiple times within the approach, step by step, right? So I'll just give here priority queue. This is fine. Priority queue linked list. That is the reason I'll just give here list node. This is fine. I'll be making use of the variable min heap, named min heap here. So new priority queue here, minimum priority queue. So we have to sort this one in the ascending order based on the value, right? So I'll just give here a comma b, this one. Oh, this is Java, right? So just give me a second here. Not equals hyphen. This one we have to give a hyphen. So a dot val minus b dot val. This is fine. So this is it for the first step. So after making use of the, after we have initialized the min heap to store the nodes based on the values, right? We have sorted, we are sorting the values in the ascending order. After this step, we have to add the first node of the each list to the heap. If you have observed, this one also we have discussed in the approach multiple times. So I have said this one multiple times that we have to add the first node of the each list to the heap. We have discussed this one in the edge cases as well, right? So here in this case, I'll just go with a simple for loop here. List, we have to add the first node of each list to the heap, right? I'll just give here in this way we can write, right? List node individual node of lists. Basically it is lists, not list here. They have given lists here, right? This one I'm speaking of parameter. This is fine. We have to ignore the empty list. So let me make use of the simple if condition here. If node not equal to null, then I'll just give here min heap. So node should not be equal to null, means we have to ignore the empty lists in that case. If it is not empty, then we have to add that particular node to the minimum heap or minimum priority queue. In this case, I'll just give min heap dot add of node. This is fine. So after this step, let's make use of the dummy node to build the result list. So it will be easier for us. So that is the reason we'll be making use of the dummy node here. Let me quickly write here list node dummy equals. So linked list is completely based on the dummy node itself, most of the problems. So here let me go with new list node of, initially let's go with the dummy node 0, right? So let me make use of the variable tail as well. Tail, let me assign this one to the dummy first. So this is fine. So we have to process until heap is empty. We saw that, right? Like every step I have showed, step by step execution, every step I have showed, we have to process until the heap is empty or until the priority queue is empty, right? So for that one, let me make use of simple while condition here. When min heap is not empty, then only we have to move forward, right? We have to process until heap is empty, means we have to consider all the elements within the lists, right? So first we have to consider when min heap is not empty, right? So I'll be making use of the while loop here. Min heap, there is a property is empty, right? So I'll be making use of it. So is empty, this one, this is fine. Within the while loop, we have to extract the minimum node, right? We have to extract the minimum node each step. That's what we did in the approach. That one I have to articulate in the form of code. I'll just give here tail dot next, this one min heap dot poll. So I'll be making use of, I have made use of the poll property here, right? So because we have to extract minimum in the each step. We have seen this one. We know this one by now, right? So we are extracting the minimum node. So the next step after extracting the minimum node, we have to move the tail pointer. So I'll just give here tail equals tail dot next in this case. This is fine. So the next step here is we have to push the next node of the extracted list, right? So we have to push the next node of the extracted list. So for that I'll just write simple if condition. I'll go with tail dot next. If it is not equal to null, then what we will do? We have to push the next node of the extracted list, right? So I'll just go with the min heap dot add. I'll just make use of the add property here. I'll just give tail dot next. Simple, right? So this is simple to understand. The final step here is we have to return the merge sorted list. So we have to ignore the dummy. So we have just made use of the dummy so that it will be easier to compute, right? So that is the reason. So now we will ignore the dummy and we have to return the merged sorted list. In this case, I'll just give dummy dot next. This is fine. This is it for the code. Let me format the code once and let me hit the run button. So here you can clearly see the sample test cases are getting passed. Means the code works absolutely correct in this case. Let's see whether this works for all the test cases or not. I have hit the submit button. Yeah, now you can clearly see all the test cases are getting passed. Means the code works absolutely correct on all the cases, for all the cases, right? So this is fine. Now let's quickly discuss the complexities for the code that we have written. So the approach that we went with here is minimum priority queue or min heap, or minimum priority queue itself, right? So this is fine. So overall time complexity would be here big O of n log k. We can just give here k. Why? Because k is nothing but number of lists here, right? So k is nothing but number of lists here. Basically, n is nothing but total number of nodes, or total nodes we can just call this one. We can just consider n as total nodes, and k is nothing but number of lists here, right? So each node is inserted and removed from the heap log k times, basically. So we are doing that. Each node here, you can clearly see this one. Each node is inserted and removed from the heap and logarithmic k times, right? So overall time complexity here would be big of n log k. Simple to understand. This is fine. So what would be the space complexity here? Overall space complexity would be big of k here. Why it is big of k? Because heap stores at most k elements at a time. Heap stores at most k elements at a time, leading us to the big of k space complexity here, right? So this is fine. So the time complexity is big of n log k and the space complexity is big of k in this case, right? So I hope the complexities are clear, and I hope whatever the code that we have written is completely clear as well, right? For now, this is it. Thanks for watching.